My talk is about node connectivity terminal backup, separately capacitated multiflow, and discrete convexity. This is a joint work with Hiroshi Hirai. First, let me introduce our problem, node connectivity terminal backup problem. We are given an unrestricted graph G with terminal set S, and upper edge capacities, node capacities, edge costs, and requirements on the terminal. Then, the goal of this problem is to find a minimum cost integral edge capacity x bounded by u, satisfying for each terminal S, there exists an integral flow from S to other terminals, capacity by x and c, with flow value R of S. In this figure, within the edge capacity x, there exists a flow from S1 to other terminals with flow value R of S1, and also exists a flow from S2 to other terminals with flow value R of S2. This problem models the situation that each terminal has its data on if the terminal fails, then the terminal must back up its data to other terminals using this network. So we want to design a minimum cost network satisfying this requirement. If all requirements on terminals are 1, then the problem is called simply terminal backup problem. It is introduced by Anshelevich and Kargyazova, and also shown its polynomial time solvability. For general requirements R, if each node is uncapacitated, that means C is equal to infinity, then the problem is called edge connectivity terminal backup problem. Moreover, if each edge is also uncapacitated, then the problem is solvable in polynomial time. But for general edge upper capacity U, it is open. That is, whether it is in P or NP hard is not known so far. For the node connectivity version, the most general version, then Fukunaga gave a 4/3 approximation algorithm, which is LP based. Fukunaga's algorithm is based on the Fractional NTB, which is a natural LP relaxation of NTB. Fukunaga showed Fractional NTB has the half integrality property, so by rounding an optimal fractional solution, we can obtain 4/3 approximate solution of NTB. For edge connectivity version, there exists a connection between fractional NTB and some kind of minimum cost multiflow. Please see this figure. Actually, fractional ETB is equivalent to find a minimum cost edge support of some kind of multiflow, which means we can decompose the edge support X into some multiflow. Hirai showed this connection by using the classical Lower-Shilkovsky theorem, which states the maximum value of multiflow is equal to the sum of minimum edge cut value. By utilizing this connection, Hirai obtained the combinatorial weakly polynomial time algorithm for FNTB and multiflow problems. Our results are extensions of Hirai's previous results on fractional edge connectivity terminal backup problem to fractional node connectivity terminal backup problem. We propose first combinatorial polynomial time algorithm for fractional NTB, and We also find a connection with fractional NTB with a new kind of merge flow, which we call separately capacitated merge flow. I will explain it in the next slide. We also find the Lovász-Cherkassky type theorem, which means the Maxwell-Minka type theorem for separately capacitated merge flow. Here we explain separately capacitated merge flow. In this merge flow setting, again we are given an undirected graph G with terminal set S, and edge capacity is U and node capacity is C. Then a merge flow F is a separately capacitated merge flow if it satisfies the following conditions. The first condition says the total flow value of F on each edge E is at most its edge capacity UE. For explaining the second condition, we first introduce Fs. Fs is the restriction of F on path connecting S to other terminals. Then the second condition says for each S, the total flow value of Fs on each node I is at most its node capacity Ci. In this figure, consider the flow value of each path is 1/2. So the total flow value of F on node I is 3/2, which exceeds its node capacity 1. But if we restrict flow F on path connecting S1 to other terminals, then the total flow value on I is 1. For any other terminals, the same thing holds. So this flow satisfies the second condition on node I. For this merge flow, we show the following theorem, which extends the Lovász-Cherkassky's theorem. The theorem says the maximum value of separately capacitated merge flow is equal to the sum of minimum cut. Here, the cut means the edge subset, pair of edge subset and node subset. So we can remove edge subset and node subset simultaneously to divide S from other terminals. Okay, in the rest of my talk, I will explain our algorithm for FNTB. Our algorithm is based on two technical ingredients. The first one is the combinatorial duality for FNTB. As I will explain later, the combinatorial dual of FNTB is the problem that maps each node on G to a subtree of this special tree, which we call infinite K-star. Then, this combinatorial dual problem is the optimization problem on this space, which we call subtree space, denoted by S. The subtree space is created by this k-dimensional grid graph and this half plane. We attach these half plane to each axis of this k-dimensional grid graph. So this half space is attached to this S2 axis. In intuition, the point on the point in this k-dimensional grid graph corresponds to this type of subtree that includes the origin in this subtree. And the subtree in this half plane corresponds to this type of subtree, which does not contain the origin. Okay, actually, the combinatorial dual problem, dual of FNTB, is actually the scope is in the scope of the concept of discrete convex analysis, on median graphs, which is our second technical ingredient. Then, in this theory, we can optimize the function by using the general method, steepest descent algorithm. In intuition, in this SDA framework, we optimize the function by the following steps. We first initialize by any subtree, and in each iteration of SDA, we update this subtree like this, and like this. Then we finally can obtain the optimal solution. By combining this SDA framework and sensitivity and constant scaling method, then we can obtain the weakly polynomial time combinatorial algorithm for FNTB. But in this talk, we omit these sensitivity and constant scaling method due to the time constraint. Okay, now we explain more details about the combinatorial duality of FNTB. Here is the combinatorial dual problem of FNTB. As we already explained before, the problem takes P as variables. P is a mapping from the nodes on G to a subtree space. So I is mapped to a subtree Pi, and J is mapped to a subtree Pj, and I prime is mapped to a subtree Pi prime, which only contains one node. And for each terminal S, PS is a node on the F branch of the infinite K-star. So S1 is mapped to a node on the S1's branch, and S2 and S3 is also mapped to these points. Okay, the objective function of this optimization problem is this form, and plus denotes this function. There are two functions defined in subtree spaces. One is d, and the other is size function. These are defined as follows. D is the minimum distance between two subtrees. So d of pi prime is this length minimum distance from pi to pi prime. And the size function is defined as follows. For a subtree that does not contain the origin, the size of pi is this length. And for a subtree that contains the origin, the size function is defined as the sum of this length, A, B, C. But why this somewhat strange formulation arises as the combinatorial dual problem of FNTB? Here is the derivation of our dual problem. First, recall that FNTB is defined by using the flow form, such like there exists a flow from each terminal S to other terminals with flow value R of S. By Menger's theorem, the condition can be represented by a cut form like this. And here we use X hat. X hat is a biset, and the biset is defined by a pair of two subsets, and this X is contained in X plus. So X is like this, and X plus is like this. And we only consider those bisets. CS is defined by all bisets such that it only includes S, and it does not include any other terminals. So so the biset is like this form. Now we also defined gamma x hat as the difference x plus minus x, and delta x hat we related delta x hat to the edge set connecting x to v minus x plus. So biset, it is known that biset is useful to represent vertex node connectivity. So by removing these delta x hat, this edge subset, and gamma x hat node subset, then the remaining graph, there does not exist a path from this terminal S to other terminals. So this defines edge and node cut. So by Menger's theorem, FNTB is equivalent to this form. Then we can take its natural LP dual, and its dual problem, it takes variables on this biset fund. We omit details, but we can apply uncrossing argument to support of pi. Then we can obtain a laminar biset family like this. Then for each node I, by using the information of the position of I in this laminar family, we can define its subtree valued potential. So for I, we can define Pi as its potential, and for J, we can define its potential Pj like this. But we omit the details in this talk. So so this is how to arise the subtree valued potential in our dual problem. Here we explain how to optimize our dual problem. In the rest of my talk, we denote its objective function of dual problem by simply f, and I recorded S is the subtree space of the infinite case. Then the dual problem is like this. Then we can simply consider this kind of cut descent type algorithm. We first initialize P by any potential P0, and in each iteration of the algorithm, find a certificate of the optimality of P, or a neighbor of P satisfying this condition, FQ is smaller than FP. We doesn't define neighbor of P, but please imagine that the natural neighbor of the grid graph. Then, if a certificate exists, and or if we find a certificate, then P is optimal. Otherwise, if we does not find a certificate and we find a Q satisfying this condition, then we update P by Q. Actually, we can show that F is bounded. We omit the proof of it, but F is bounded. So if we do this part, then the algorithm terminates in finite steps, and we can find the optimal potential for the dual of FNTB. We show that this part can be done by calling a max flow algorithm. In intuition, by using complementary slackness condition, we can reduce this part to a feasibility of a circulation problem. Then a circulation problem can be solved by using a max flow algorithm, and we can find a feasible circulation, or a violating cut that certify that there does not exist any physical circulation. Then a circulation becomes a certificate of this optimality. And a violating cut becomes gives rise to this Q, this neighbor of P, satisfying this condition. And also, moreover, a certificate, so which is a circulation of this problem, is actually an edge support of separately capacitated multiflow. So this circulation actually gives rise to an optimal solution for our primary problem, FNTB. So this algorithm becomes a pseudo-polynomial time algorithm for FNTB, and we can also derive the previous Maxwell-Minka theorem for separately capacitated multiflow. Actually, we can improve the evaluation of the number of iterations of the previous cut descent algorithm by using the notion of discrete convex analysis, or our second technical ingredient. The key point is the combinatorial dual problem of FNTB is a minimization of an L-convex function on this discrete structure, this substrate space. In other words, S is a median graph, a special graph class, and f of p is an L-convex function, a special function class on the product of substrate spaces. In discrete convex analysis, or in its extension beyond integer lattice, there exists a steepest descent algorithm framework for minimization of L-convex functions on special graph classes. These classes include trees, product of trees, grid graphs, and median graphs, etc. Then we can show that the previous cut descent algorithm is precisely this SDA. So by using the DCA theory, the number of iterations can be shown to be order NA. Here A is the maximum edge cost, so it remains a pseudo-polynomial time, but we show a new sensitivity result. So, and by combining its sensitivity result and cost scale method, we can improve the time complexity to weekly polynomial time. Okay, this is the conclusion of my talk. Our algorithm is about the fractional node connectivity terminal backup problem, FNTB, and its dual problem is actually a minimization of an L-convex function on substrate space, which is median graph. So we can apply the SDA framework from the theory of discrete convex analysis, and by combining it with new sensitivity result and cost scaling method, we can derive a weekly polynomial time algorithm for FNTB. And we also derive a Maxwell-Minka theorem, which extends the classical Lovász-Cherkassky theorem for free multiflow to separately capacitated multiflow, which is a new variant of multiflow. Okay, and finally, we mention further research directions. The first one is an extension of our method to fractional node terminal backup problem to the fractional node connectivity survivable network design problem. And the second one is the flow augmenting type proof of the Maxwell-Minka theorem. Maxwell-Minka theorem is this. Yeah. Now our proof of this Maxwell-Minka theorem is algorithmic, and it is via this algorithm, this algorithm for FNTB. So we think that flow augmenting type proof also exists. And it is also interesting to investigate the integer version of separately capacitated multiflow. Okay, this is the end of my talk. Thank you for listening.